Assalamualaikum. Today we are going to present to you about volumetric analysis of titration in pharmaceutical industry. But before that, we are going to introduce ourselves first.
What is a volumetric analysis? Volumetric analysis is a quantitative method in chemistry used to determine the concentration of a substance in a solution by measuring the volume of another substance required to react with it. This often involves titration, where a solution of known concentration is added to the solution being analyzed until a chemical reaction is complete. The volume of the added solution is used to calculate concentration of unknown substance.
What is titration? Titration is a versatile and widely employed analytical technique that plays an important role in quantitative chemical analysis. It involves the controlled addition to a solution of a known concentration that called titrant to a solution of the substance that being analyzed that called analyte until a chemical reaction between two samples is completed. The key objective of titration is to determine the precise amount of the analyte, allowing for the calculation of its concentration. The basic component of a concentration: first, titrant, the solution of known concentration added to the analyte. Second, analyte, the substance that being analyzed, the concentration is unknown. Third, indicator. Indicator is used to determine the endpoint of the titration. And fourth, the endpoint is the point where the reaction between titrant and analyte is completed, indicated by noticeable change in color or pH.
What is a direct titration and back titration? Direct titration is a titration when there is a direct addition of standard titrant with known concentration and volume into an analyte with the presence of acid-base indicator until reaction is completed and reach its equivalent point. While a back titration involves reacting an analyte with excess of reactant of known concentration. The excess reactant is then titrated against a standard solution.
Advantage of titration. First, precise measurement. Titration allows for accurate determination of the concentration of a substance in a solution. Second, versatility. It can be applied to various types of chemical reaction and is widely used in analytical chemistry. Third, cost-effectiveness. Titration is often more economical than other methods for analyzing concentration. The advantage of titration. First, time-consuming. The process of titration can be time-intensive, especially when dealing with complex samples. Second, scale-dependent. Accurate results rely on the skill of the operator, and human error can impact the precision of the analysis. Third, limited applicability. Some substances may be not be suitable for titration due to lack of a suitable indicator or other constraints.
An experiment for titration in the pharmaceutical industry can be designed to determine the concentration of a specific active pharmaceutical ingredient, API, in a drug formulation. So let's outline a simple experiment for the assay of acetyl salicylic acid aspirin using a basic titration setup. So this is the example of the procedure. The first one is we need to prepare the sodium hydroxide solution of known concentration, standardize the solution if necessary. The second one is we need to do sample preparation, crush and green a pharmaceutical tablet containing acetyl salicylic acid to ensure uniformity, weight and appropriate amount of powdered tablet. The third one is dissolution of acetyl salicylic acid. Dissolve the weighed acetyl salicylic acid in a simple conical flask using a small amount of distilled water, ensure complete dissolution. The fourth one is we need to do titration setup. Pipette a measured volume of the acetyl salicylic acid solution into an Erlenmeyer flask. Add a few drops of phenolphthalein indicator. And the fifth one is we need to do titration. Fill the burette with the standardized NaO solution. Slowly titrate the sodium hydroxide solution into the acetyl salicylic acid solution with constant swirling until a faint pink color persists for at least 30 seconds. The pink color indicates the endpoint. The sixth one is record the data. Note the additional and final burette readings. The volume of sodium hydroxide solution used represents the amount of required to neutralize the acetyl salicylic acid. And the last one is calculation. For calculation, use the volume and concentration of the sodium hydroxide solution to calculate the moles of sodium hydroxide. Since the reaction is ratio 1:1 with acetyl salicylic acid, the moles of sodium hydroxide are equal to the moles of acetyl salicylic.
I want to tell you the results on this experiment. I can provide a general outline of how the results might be interpreted, but keep in mind that the actual results would depend on the specific details of the experiment, such as concentration used and the accuracy of measurements. Let's assume hypothetical values for the sake of illustration. Concentration of now solution 0.1 molar, volume of now solution used 25 ml, moles of now solution that used from titration 0.1 molar times 0.025 L equal to 0.0025 moles. Since the reaction between now and aspirin is 1:1, the moles of aspirin are also 0.0025 moles. So the calculation is if the weight of the tablet was used, for example 0.5 grams, and the molar mass of aspirin is approximately 180 gram per moles, moles of aspirin in the tablet is 0.5 gram divided by 180 gram per mole equal to 0.0278 moles. The concentration of aspirin in the tablet is concentration equal to moles of aspirin divided by volume of tablet solution in liters. So 0.00278 mole divided by 0.025 liter equal to 0.1112 molar. The concentration of aspirin in the pharmaceutical tablet is approximately 0.1112 molar. This results indicates the amount of the active pharmaceutical ingredient present in the tablet. Okay, now I want to tell you the discussion of this experiment. The accuracy and precision of the results obtained in this experiment were crucial factors in determining the concentration of aspirin in the pharmaceutical tablet. Potential sources of error, including equipment, calibration, and measurement precision, were considered. By comparing this experimentally determined concentration with theoretical or label values, deviations were identified, prompting consideration of potential manufacturing issues. The validity of the titration method was evaluated based on its ability to consistently provide reliable results. The experiments compliance with pharmacopoeia standards and regulatory requirements was emphasized to underscore its relevance to industry guidelines. The implications of the determined concentration on the drug's efficiency were considered, ensuring it falls within the therapeutic range for optimal effectiveness. Suggestions for improvement and optimization focus on refining accuracy, efficiency, and particularly for large-scale manufacturing. The experiment's contribution to regulatory compliance was highlighted, emphasizing its alignment with pharmaceutical quality control practice. In summary, the discussion underscores the reliability and validity of the titration method for aspirin acid assay, affirming its suitability for routine use in the pharmaceutical industry while acknowledging areas for potential enhancement.
Titration in pharmaceutical industry. Titration is widely used technique in the pharmaceutical industry for quality control and analysis of pharmaceutical products. Gradual addition of titrant to a sample solution until a specific endpoint is reached. The endpoint is typically indicated by the change in color. The choice of titration method depends on the specific analytical requirement of the pharmaceutical product being tested. Titration application in pharmaceutical industry. First, as an assay for active ingredient. Titration used to determine the concentration of the pharmaceutical ingredients in drug formulation and to ensure that the pharmaceutical product contains specific amount of active compound, guaranteeing their efficiency. Second, quality control. Pharmaceutical product must meet strict quality control standard to ensure safety, efficiency, and consistency. Third, water content determination. There are specialized forms of titration to determine the water content in drug and drug substance, that is Karl-Fischer titration. Fourth, regulatory compliance. Titration data is often a key component of the documentation required for regulatory submission, demonstrating that the product meets established specifications. Conclusion: titration plays important part in the field of analytical chemistry, holding the paramount of importance in various industries, particularly in the pharmaceutical sector. Its versatility, precision, and reliability makes it an indispensable tool for a range of applications critical to pharmaceutical development, manufacturing, and quality assurance.